Let us investigate transport systems now. The lipid cell membrane provides a barrier against the transport of hydrophilic molecules into or out of the cell. Ion channels are selective pores in the membrane that allow the ready transfer of ions down their electrochemical gradient. The open-closed state of these channels is controlled either by the membrane potential, voltage-gated channels, or by transmitter substances, ligand-gated channels. Some channels, for example calcium channels in the heart, are both voltage and transmitter-gated. Voltage-gated channels for sodium, potassium, and calcium have the same basic structure, and subtypes exist for each different channel. Important examples of drugs that act on voltage-gated channels are calcium channel blockers, which block L-type calcium channels in vascular smooth muscle and the heart, and local anesthetics, which block sodium channels in nerves. Some anticonvulsants and some antiarrhythmic drugs also block sodium channels. No clinically useful drug acts primarily on voltage-gated potassium channels, but oral antidiabetic drugs act on a different type of potassium channel that is regulated by intracellular adenosine, triphosphate, ATP. Active transport processes are used to transfer substances against their concentration gradients. They utilize special carrier molecules in the membrane and require metabolic energy. Let's discuss two examples here. Example number 1, sodium pump. This expels sodium ions from inside the cell by a mechanism that derives energy from ATP and involves the enzyme adenosine triphosphatase, ATPase. The carrier is linked to the transfer of potassium ions into the cell. The cardiac glycosides act by inhibiting the sodium or potassium ATPase. Sodium and chloride transport processes in the kidney are inhibited by some diuretics. The second example is norepinephrine transport. The tricyclic antidepressants prolong the action of norepinephrine by blocking its reuptake into central nerve terminals.